SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied. Today we shall discuss about the thermal analysis of CI engine. If we recall, in the last class we have discussed about the performance of Otto cycle, and to do that we had to consider several processes those constitute together to form the Otto cycle. So, today since we need to discuss about the thermodynamic performance of CI engine, and you all know that the processes of CI engine are analyzed by comparing them with an air standard cycle. That means, the processes which are there in a CI engine, those processes together constitute a cycle, and if you would like to analyze the cycle performance, we need to compare that cycle with a standard with an air standard cycle, and the air standard cycle which is used to analyze the performance of CI engine is known as diesel cycle. So, before going to discuss about, rather before going to derive the efficiency, rather thermal efficiency of the diesel cycle, let us briefly look into the processes which are there in a CI engine. So, if we draw the schematic of a CI engine, so we shall discuss now. This is intake valve and this is exhaust valve. The first stroke is the intake stroke, and during this stroke piston travels from top dead center to the bottom dead center, while the exhaust valve is remaining closed, but intake is open and fresh air is drawn into the engine cylinder. So, that is the intake stroke. Next stroke is the compression stroke. So, when piston is at BDC at the end of the intake stroke, exhaust valve is already closed, intake valve is now closed, and piston travels from BDC to TDC, and the air which is drawn into the cylinder during intake stroke is now getting compressed. So, that is the compression stroke. When piston is about to reach at TDC, during the end of the compression stroke, both valves are closed. What is done? Fuel is supplied or fuel is injected into the cylinder in the form of spray, and that is what I had tried my best to show the spray pattern. And when piston is at TDC or little away from TDC in the next stroke, entire combustion is completed. And when the combustion is completed, as we know what we have discussed in the Otto cycle, in the context of Otto cycle, that it is because of the rise in pressure and temperature of the working substance, the thrust which is being applied on the piston face is the responsible force for the movement of piston from TDC to BDC, that is the power stroke. So, this is basically power, and sometimes it is known as expansion. So, basically what is happening, you know, that when piston is at TDC or piston is again travelling back from TDC to BDC after the compression stroke, combustion would be completed, and it is because of this combustion, you know, the rise in temperature and pressure of the working substance which is there inside the cylinder will create a thrust on the piston face, and that is the driving force for the, you know, movement of piston from TDC to BDC again, and that is the power stroke. So, it is getting, you know, the combustion gases which are there inside the cylinder is now is now getting, you know, expanded. So, combustion gases which are there inside the cylinder are now getting expanded because of the movement of piston from TDC to BDC, right. And when again piston is coming towards BDC, you know, before it reaches at BDC, exhaust valve is allowed to open, essentially to take blowdown. So, the purpose is, you know, to reduce the pressure inside the engine cylinder, gas pressure inside the engine cylinder. So, when piston is about to reach at BDC during power stroke, during end of the power stroke, exhaust valve is allowed to open. The sole purpose is to reduce the pressure inside the cylinder, gas pressure inside the cylinder combustion chamber, so that when piston is again coming back from BDC to TDC in the next stroke, it will experience relatively lesser resistance. So, when exhaust valve is allowed to open, certain amount of, you know, combustion gases will leave out from the combustion chamber or cylinder, and while the combustion gases are leaving from the engine cylinder, those gases will carry certain amount of energy. So, it is called blowdown or heat rejection. And finally, when piston is again travelling back from BDC to TDC, intake valve is remaining closed, but exhaust is now fully open, and what will happen, you know, that it is called exhaust stroke. So, the combustion gases, you know, those are there inside the chamber, combustion chamber or cylinder, will now, you know, goes out, will now leave from the combustion chamber. So, combustion gases will go out from the combustion chamber or cylinder, engine cylinder during the exhaust stroke. So, we have understood all these strokes, and if we try to map all these processes in PV and TS plane, because we have discussed in the last class, to establish the mathematical expression of thermal efficiency, we need to map all these processes in different thermodynamic planes. What are those different planes? One is PV, another is TS. And we have discussed, you know, that the TS plane is very important, you know, because the area under the process line in TS plane will, you know, give us the heat interaction. So, from there directly, without going for any mathematical calculation, but just by knowing the process line, and if we can draw the area under the process line from that plane, we can calculate what is the amount of heat being supplied to the system and the amount of heat being rejected from the system. From there we can quantify the thermal efficiency. One important part is, you know, that in the context of Otto cycle we have discussed that the combustion process, which is very important, and this process as if is providing certain amount of heat to the system. So, when we had tried to represent that particular process in PV and TS plane, in particularly in PV plane, that is a kind of constant volume heat addition, that is what we have discussed in the context of Otto cycle. But can we again represent that particular process, that is combustion process, by a constant volume heat addition in PV plane pertaining to this cycle, that is diesel cycle or not, that is what I would like to discuss briefly over here. You know that what we have discussed in the context of Otto cycle is that when piston is reaching a TDC, you know, for the Otto cycle SI engines, you know that it is not a pure air, rather it is charge, air fuel mixture. So, air fuel mixture is getting compressed when piston is travelling from BDC to TDC, both valves are closed, and when piston is reaching a TDC or about to reach a TDC, we need to switch on the spark plug, and the moment when spark plug switch is on, then it ignites the total charge, that is, you know, remaining inside the cylinder in a, you know, as a compressed state. So, that particular, you know, situation, you know, ensure that the entire combustion should be completed when piston is remaining close, you know, at TDC, though it is very unlikely that you know, the movement of the piston is spontaneous. So, it is not possible that we can keep the piston there for a while when it is reaching a TDC and entire combustion should be completed, but the assumption of constant volume combustion, that is when piston is reaching closer to TDC and we need to switch on the spark plug, and the moment when spark plug switch is on, the entire charge will be combusted, and as if at that time piston is reaching at TDC and it is remaining there, I mean during that time. So, momentarily when piston is reaching at TDC, entire combustion would be completed, and as if the volume is remaining constant. So, it is a constant volume combustion, but for the SI, for the CI engines or the, you know, diesel cycle, what we are going to discuss, that is what we are going to discuss today. You know that it is not possible to represent that combustion process by a constant volume heat addition. Why? You know, piston will be reaching at TDC. In fact, even if we start spraying fuel when piston is about to reach at TDC, then also it is not possible to mimic the process of combustion by a constant volume, because we have discussed two important things. One is called physical delay, and it has two different components. We have discussed about the ignition delay, and it has two components, one is physical delay, another one is the chemical delay. So, these two different delays constitute together the ignition delay. So, if we allow, even because, you know, nozzle is a mechanical device, so this particular device needs finite amount of time to spray certain amount of fuel per cycle into the engine cylinder. So, at that, during that particular time, it is very unlikely that the piston will remain exactly at TDC and the volume will remain constant. Instead of considering that, instead of considering the constant volume combustion, I mean combustion by a constant volume heat addition process, for the CI engines, what is, you know, considered is that piston is, when piston is about to reach at TDC, fuel, you know, supply to the engine cylinder is started, and the first phase, the fuel being supplied during first phase will be combusted, and it is because of this combustion, you know, there will be certain amount of rise in pressure inside the cylinder, and when piston is again travelling back from TDC to BDC towards BDC, entire combustion would be completed, and the pressure as if should be, you know, the cumulative effect of this should be such that the pressure inside the cylinder is remaining more or less constant instead of volume. So, as I said, movement of the piston is very spontaneous, and, you know, it is very difficult to assume that the piston will be there at TDC and during that time entire combustion will be completed, and this is not possible accounting for this ignition delay, because the supply of total amount of fuel that is needed per cycle is it is required certain amount of time. Also if we can ensure that the fuel is supplied in proper time, accounting for the chemical delay that we have discussed, it will take certain amount of time for the total combustion, and at that time piston again will come back from TDC to BDC. If it is the case, you can see that piston is reaching towards TDC and again coming back from TDC. So, volume will not remain constant. So, it is very difficult to assume the process by a constant volume heat addition process. Instead, what we can do, we can assume that the pressure which is being developed during the supply of first phase of fuel, that will take part in the combustion, and it is because of this first phase of combustion a rise in pressure will be there. So, that pressure is such that when piston is again coming back from TDC to BDC, you can argue with me that the pressure will fall, but at that time again second phase of combustion has already started. So, as if the pressure is remaining constant more or less during the entire process, and that is why the combustion process of a CI engine is represented by a constant pressure heat addition process in PV plane. So, that is what is very important to remember. So, now if we draw the PV and TS plane, that is very important to analyze. So, this is P, this is V, this is S, and this is T. So, if we assume this is so, this is VBDC, this is VTDC, and say this is the intake process, constant pressure air intake, and if we say this is point 1 when piston is again coming back from BDC to TDC, that is the compression process, and that process, as I said, that we are trying to analyze all the processes using an air standard cycle, and that is the diesel cycle, and we are assuming that the working substance is behaving just like an ideal gas, and we can use ideal gas equation to know the pressure and temperature at the end of different processes. So, this is the compression process, and we have discussed in the last class that this is represented by an isentropic compression process. So, this is a 1 2 and 2 to 3 when piston is at BTDC, as I said that combustion will start, but combustion will last till piston has started travelling from TDC to BDC, and as if the pressure is remaining constant, accounting for the rise in pressure during both first phase of combustion and last phase of combustion. And this is the point 3, and you can see that it is not a constant volume combustion. The combustion is not represented or mimicked by a constant volume heat addition process, because volume is getting changed instead, but pressure is remaining constant. And finally, 3 to 4, so this is the expansion or power stroke, and 4 to 1, you know that when piston is about to reach at BDC, volume is remaining more or less constant. What we need to do, we need to open the exhaust valve to take certain blow down of the combustion gases, only to reduce pressure inside the cylinder, and this blow down process as if is the representative measure of heat rejection from the system. So, basically that is 4 to 1, so that is Q out. So, again I am writing 5. So, the points 5 and 1, these 2 points coincide each other. And again when piston is coming back from BDC to TDC, exhaust valve is now fully open, the 5 to 6. So, 6 to 1 was the constant pressure intake that we we have just mentioned, and finally 5 to 6 is constant pressure blow down. So, these two processes are thermodynamically same. So, we have no need to consider these two processes while analyzing the thermal performance of this cycle. And this 2 to 3, so this is Q in. So, constant pressure heat addition, and if we draw, so 1 to 2 is isentropic process. So, 1 to 2, three to 4. 3 to 4 is again isentropic expansion, 1 to 2 isentropic compression and 3 to 4 isentropic expansion. So, this is isentropic expansion, and this process isentropic compression. Okay. So, now we can just go for the calculation of pressure and temperature at the beginning and at the end of each process, and from there we can quantify. One thing I would like to tell you, so you can see that this V4 equal to V1 equal to VBDC and V2 equal to VTDC, and VBDC by VTDC, that is the compression ratio. So, compression ratio RC equal to VBDC divided by VTDC, that is what we have discussed in the in one of the previous classes. Now, so we can now go for the calculation of the thermal efficiency, right. One thing I would like to tell you that you know that here process 2 to 3 is basically the combustion process, and as if this process is represented in this PV plane by a constant pressure heat addition process, and in this process we can see from this PV plane is that there is a change in volume, right. So, in this process, rather in the process of combustion, volume of the working substance is getting changed from V2 to V3. So, the ratio of this change in volumes is known as cut-off ratio pertaining to the combustion of CI engines. So, if we write in the next slide that cut-off ratio beta, that is equal to V3 by V2, we are interested in the specific volume. So, this is V3 by V2, and since we are utilizing the ideal gas equation, we can write it T3 by T2. So, this is very important. So, if we analyze the first process now, so the change in, there is a change in volume of the working substance during the combustion process, and that is what we have discussed, that it is very unlikely to expect that the piston will be there at TDC, and during that momentarily all the entire combustion would be completed. It is not a case for this particular type of engine, because the supply of fuel into the combustion chamber, which is an essential element for the combustion, would require a finite amount of time accounting for the ignition delay, and it is because of this delay volume is going to change during the combustion process, but we can represent this process by constant pressure heat addition process, and this is a very good assumptions that I can tell you, because there will be a rise in pressure during first phase of combustion, and that pressure perhaps will be reduced as the piston is travelling from TDC to BDC, but the rise in pressure due to second phase of combustion will compensate that rise in pressure, and as if the pressure is remaining constant during the entire process of combustion, and that is represented by this, right. So, what we can see from here is that the T3 equal to T max. So, when the combustion process is completed, the rise in temperature is the rise in temperature will lead to the maximum temperature, and that is T3. Similarly, P3 equal to P max equal to P2. P2 is also equal to P3, because momentarily that pressure is remaining constant, and this pressure is almost the maximum pressure of this cycle. Okay. So, if we go to the first process, so process 1 to 2, that is isentropic compression, right. Isentropic compression, both valves are closed. I am not going to write that, and we can write T2 equal to T1 V2 by V1 power k minus 1. So, this is very important, and okay. So, I did little mistake here. So, this would be V1 by V2. So, let me write here like this, V1 by V2 equal to T1 into small V1 by V2 power k minus 1. If we go back to the previous slide, as I told you, V1 equal to VBDC and V2 equal to VTDC. So, V1 by V2 is essentially VBDC by VTDC, that is RC, that is the compression ratio. So, this is the compression ratio. Compression ratio. Okay. So, that is T1 into RC power k minus 1. Similarly, we can write P2 equal to P1 into V1 upon V2 power k equal to P1 into small V1 upon small V2 power k, that is P1 into RC power k, right. And what is the work done? Because this is the compression process, so we need to supply work into the system. So, basically W1 to 2, that is P2 V2 minus P1 V1 upon 1 minus k, that is R T2 minus T1 upon 1 minus k. Just applying first law for the non-flow system, we can write a first law for the non-flow process. So, first law applied to the non-flow process, we can write, that is U1 minus U2. So, that is CV into T1 minus T2. So, this is the work done. And what about heat interaction? Because the process is isentropic, so there is no heat interaction between the system and surroundings. So, there is no rise in temperature, there is no heat interaction. So, basically the rise in temperature that is there due to compression process, but there is no heat interaction from the system into the surroundings. So, Q1 to 2 equal to 0. If we go to the next process, so process 2 to 3, and that is constant pressure heat addition or constant pressure combustion. So, this is constant pressure combustion. We have seen that we have written beta 2, that is change in volume V3 by V2, that is the cutoff ratio, that equal to T3 by T2, right. what is Q23? Q23, because we are interested in the rise, rather increase or addition of heat into the system, that is I can write in specific form, that is Cp into T3 minus T2. Why it is Cp? Because the process is constant pressure process, constant pressure process, right. So, I can write Q23 equal to mass of air plus mass of fuel into Cp into T3 minus T2. So, from there we can write Q23 equal to like this, equal to change in enthalpy H3 minus H2. What about work done? So, if we try to recall the combustion process for the Otto cycle, in that case we could write Q23 equal to Cv into T3 minus T2, that was constant volume process. So, instead of Cp we could write Cv. Also we could write that no work done, constant volume process, but this is a constant pressure process. So, what will be the work done? Again, if I write first law for the system, that is for the non flow process, we can write W23 equal to Q23 minus U3 minus U2, del Q equal to del W plus du. So, del Q equal to del W plus U3 minus U2, and if I take W23 here, because heat and work, these two are inexact differential, they are not exact differential, they are path function. So, if we write for if we write the expression for this process 2 to 3, then W2 to 3 equal to Q23 minus U3 minus U2. So, that is the work done, right. So, and that is equal to P2 or P3 into V3 minus V2. Okay. So, what I can write over here, it is very important to mention that. So, this is the quantity. So, this is the heat addition Q in the cycle. So, this is the heat addition to the cycle Q in. So, I have written here because I will be using this expression later. Next is process 3 to 4, and this is again isentropic expansion. So, we can write T4 equal to T3 into V3 by V4 power k minus 1 equal to T3 into small V3 by small V4 power k minus 1. Similarly, we can write P4 equal to P3 into V3 by V4 power k equal to P3 into small V3 by small V4 power k. So, this is we can write the pressure and temperature at the end of the expansion process, because we know the pressure and temperature at the beginning of the expansion process, that is T3 and P3, and those are T max and P max. So, we know, and this is isentropic process. So, there is no heat interaction between system and the surroundings, but what is the work interaction? W324 equal to P4 V4 minus P3 V3 upon 1 minus k, that equal to R into this very important, that equal to R into T4 minus T3 upon 1 minus k, and that is nothing but U3 minus U4 equal to CV into T3 minus T4, right. So, again if we write the that we can write del cube equal to del W plus del U. Therefore, del cube equal to del W plus du. So, this is equal to 0. So, W 2 to 3 equal to W 3 to 4. U3 minus U4, right, and that is what we have used. So, that is what we have used over here, fine. And if we go to the final process, that is the process 4 to 5 or 4 to 1, because points 5 and 1, these 2 points coincide each other. So, if we write process 4 to 5, that is constant volume heat rejection. Why it is heat rejection? Because as I said that blow down is taken at constant volume only to reduce pressure inside the cylinder, and during this process when gases are leaving from the cylinder, those gases are carrying certain amount of energy from the system. So, as if heat is getting rejected, and it is very important that second law of thermodynamics puts a restriction that there must be a heat rejection if we need to run the run all this process in a cyclic manner. So, this is heat rejection. What we can write that so this is constant volume process. So, work done is equal to 0. We can write Q4 5 equal to CV into T4 minus T5, right, because if we go back to the previous slide here. So, point 5 and point 1. So, this is basically that T4 is greater than T1 or T5, but I should write this is T5 minus T4 equal to CV into T1 minus T4. Okay. So, this is the, again let me keep this quantity inside a box. So, this is, let me write here. So, this is heat rejection Q out, right, and if we go to the previous slide, next process is 1 to 6, and as I said that process 6 to 1 and 1 to 6, these two processes are similar thermodynamically. So, it is, we have no need to, rather it is not necessary that we should consider these two processes in the cycle while calculating, because they will cancel each other. So, even if we consider these two processes separately, ultimate consequence would be 0. So, ultimate consequence considering these two processes will be null. So, if we go to the thermal or thermodynamic performance of diesel cycle, that is equal to W net by Q in, that is Q in minus Q out by Q in right. So, that is equal to 1 minus q out divided by q in. We are interested in the absolute value of this, because heat and work, these two are in thermodynamics, these two quantities are also having certain direction. So, while we are calculating efficiency or thermal performance, we are interested in the absolute value of these two quantities, not the direction. So, that is why I have taken, I have written in this fashion. So, if we write, so q out is this Cv into T1 minus T4. So, if we go to the next slide and if we write, so eta thermal diesel equal to 1 minus q out divided by q in, that is 1 minus Cv into T1 minus T4 divided by Cp into T3 minus T2, because Q23, that is Q in equal to Cp into T3 minus T2. So, that is what I have written over here. Okay. So, I can write, that is 1 minus T4 minus T1 divided by T3 minus T2 into Cp by Cv. So, we can write 1 minus 1 upon k, and if I take T1 outside, T4 by T1 minus 1, if we take T2 outside, T3 by T2 minus 1. So, again we can write it, that is 1 upon 1 minus k, and T1 by T2, right, what is T1 by T2? So, I can directly write that beta equal to V3 by V2 equal to T3 by T2. So, this quantity is beta, right, and what about T1 by T4, T1 by T2? Now, I can write this T2 equal to T1 equal to T2 into V2 by V1 power k minus 1, and what is V2 by V1? If we go back to the previous slide, V2 equal to VTDC and V1 equal to VBDC. So, V2 by V1 is equal to 1 upon RC, right. VTDC by VBDC, V2 by V1. So, that is 1 upon V1 by V2, that is 1 upon RC. So, I can write it, therefore, I can write T1 by T2 equal to 1 by V1 by V2 power k minus 1, that is 1 upon RC power k minus 1. Okay. So, we can write it Cp by Cv equal to 1 upon k, T1 by T2. So, this quantity T1 upon T2, this T1 upon T2, this quantity can be written 1 upon RC power k minus 1. So, I am writing 1 upon RC power k minus 1, T4 minus T1 minus 1 divided by beta minus 1, right. So, we can go one step further in the next slide. So, eta thermal diesel equal to 1 minus 1 upon RC power k minus 1 T4 by T1 minus 1 by k into beta minus 1, right. So, let me write here, we know T4 equal to T3 into V3 by V4 power k minus 1 and T1 equal to T2 into V2 by V1 power k minus 1. That we know, because process 3 to 4 is isentropic expansion and process 1 to 2 is the isentropic compression. So, we know the temperature at the end of the expansion process and also temperature at the beginning of the expansion process T2. So, we can write T4 by T1 that is equal to T3 by T2 into what we can write is V3 by V4 into V1 by V2 power k minus 1. See, if we go back to the previous slide, V4 equal to V1 equal to VBDC. So, V1 equal to V4 equal to VBDC. Now, if we go to the final expression that we have written here, so this V4 equal to V1 will get this two V1 will equal to V4. So, we can cancel these two terms. So, we are left with T3 by T2 into V3 by V2 power k minus 1. And what about T3 by T2? T3 by T2 equal to V3 by V2, that is equal to cut-off ratio. So, I can write this is V3 by V2 power k, that is beta power k, because T3 by T2 equal to V3 by V2. So, V3 by V2 into V3 by V2 power k minus 1, that is V3 by V2 power k, and that is beta power k. So, if we replace the value of V3 by V2, that is T4 by T1 equal to beta power k over here, then we can write the final expression 1 minus 1 upon RC power k minus 1 beta power k minus 1 divided by k into beta minus 1. So, this is the thermal efficiency of the diesel cycle, and that we can see from this expression is the efficiency of diesel cycle is function of compression ratio as well as the cut-off ratio beta. Now, I would like to tell you one important thing. You know that I can write this eta thermal diesel equal to 1 upon 1 power RC power k minus 1 into beta power k minus 1 divided by k into beta minus 1. Now, you know this term is extra term. We had, if we try to recall the thermal efficiency of Otto cycle, then we will find that the Otto cycle efficiency is 1 minus 1 upon RC power k minus 1. So, that means, if we go to the next slide, that eta thermal diesel equal to eta thermal Otto into this extra term, that is beta power k minus 1 divided by k into beta minus 1. Right? K is always greater than 1, and cut-off ratio, if we know the definition V3 by V2, V2 is always greater than V2, always greater than 1. So, the quantity that we have written inside the bracket is always greater than 1. So, for a given compression ratio, the efficiency, thermal efficiency of diesel cycle is less than thermal efficiency of Otto cycle, right. This ratio is always greater than 1. So, the efficiency of thermal efficiency of Otto cycle is diesel cycle efficiency by something, and that something is always greater than 1, right. So, efficiency of Otto cycle is always greater than efficiency of diesel cycle, and it indicates that constant volume combustion is more efficient than the constant pressure combustion. Why? Because for the Otto cycles, we could represent the combustion process by constant volume heat addition process, but for the diesel cycle today we had seen that we could represent the combustion process by a constant pressure heat addition process. Since efficiency for a given compression ratio, of course, this is for a given compression ratio, right. Efficiency of Otto cycle is greater than efficiency of diesel cycle, which indicates that the constant volume combustion is efficient than the constant pressure combustion. But mind it, diesel cycles are diesel engines rather run with a higher compression ratio with higher compression ratios than the Otto cycle, and hence efficiency of diesel cycle should be always greater than efficiency of the Otto cycle. So, to summarize today, we have discussed about the combustion process in CI engines, and we had seen that the combustion process of CI engine can be represented by a constant pressure heat addition process, which is in contrast to the constant volume heat addition process that is there in the in SI engines. And finally, we could establish the thermal performance or thermodynamic efficiency of the diesel cycle, and we had seen that the efficiency can be is represented as a function of compression ratio as well as the cut-off ratio. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.